So a very good day once again. So we'll pick up things from where we stopped last time. And in our last class, we were able to cover a few details about the Schrodinger equation, and then we talked about the Hermitian operator. So I'll pick up things from there right quick to talk about a few properties of the Hermitian operator. Because this would be very useful, especially the first point in terms of resolving some other details. So okay. Now you'll recall that we made mention that the operator is said to be Hermitian when we are able to probably flip it over to the other side such that its inner product is the same. Should we have an expression, say, having a function that's the bra of f and the ket of the operator phi part operating on G being the same as the bra of the operator operating on F and the ket of G, if and only if phi hat is Hermitian. And in the last class, we made mention that most of the operators in quantum electronics are Hermitian, okay? That is, most of the operators in quantum electronics are Hermitian. So what are the properties of this Hermitian operator? So the first is that they always have real eigenvalues, okay? So Hermitian operators always have real eigenvalues. So in other words, it means that they do not include, let's say, let's put up, they do not include the complex operator J, okay, which is the same as the square root of -1. So here you will know that should the operator be a matrix, then the eigenfunction or the eigenvector may be complex, okay? So if, for instance, the operator is a matrix, then the eigenfunction, or better still, the eigenvector may be complex, okay? But do note that the eigenvalue is always a real value. So the eigen, now, regardless of the fact that the eigenfunction or the eigenvector may be a complex quantity, the eigenvalue is always a real number, okay? For it to be Hermitian. So, in other words, should we take things up from there, then we can now say that the physical observables such as the position, for instance, x, then the momentum, p sub x in the direction of x, then the energy are ordinary real numbers, okay? They are ordinary real numbers. Since they are the eigenvalues of the Hermitian operator. Okay, so that's one fundamental property you should take note of. Now, another property is that, let's write this. So another property is that the eigenfunctions may be chosen so that they are normalized or mutually orthogonal. And when we say two values or parameters or functions are orthogonal, it means that the inner product of those two parameters is the same as 0, which is the same as the dot product, okay? So it means their eigenfunction will be chosen so that they are normalized and mutually orthogonal. So the implication is that the they form an orthonormal set. And when we say a set is orthonormal, it means that the set of vectors is an orthogonal set of unit vectors. And then you should note that the eigenfunctions of a Hermitian operator are orthogonal. If they have different eigenvalues, okay? And I already made mention that the inner product of two functions must be zero to be orthogonal. Now, when we say inner product, what we actually mean from your vector analysis is dot product, okay? The dot product. It should be 0. And once it is 0, then it means they are orthogonal. And another property for us to have for the operator to be Hermitian is that the eigenfunctions form a complete set, okay? The eigenfunction set. So the implication is that any function may be written as a linear combination of the eigenfunctions for it to be a complete set. So if that is clear, so quickly go back. So where we stopped. And this time, we'll be looking at the Hermitian operator, for instance, the expectation value of the operator, say it is Hermitian. Now let us, so if we are given a Hermitian operator, say A hat, For us to be able to evaluate the expectation value of this Hermitian operator, then we could evaluate the time rate of change. And we already know that the time rate of change of this operator is the same as d dt integral psi of x a psi dv, where this gives us the expectation value from what we already talked about. So once the derivative function comes into the integral, so it becomes partial, then we now have something like this. Okay. And once we resolve this through product rule for what we have in the bracket, then we have, if say VDU plus UDV, so the conjugate of psi d dt a psi plus the psi conjugate dt a psi dv. Okay. And once again, using product rule for this expression, then we have that the time rate of change of the Hermitian operator is the same as integral by conjugate, now operating on this parameter here, the partial derivative, then we should get more like UDV plus VDU, right? So dt psi plus a the psi dt plus the psi spheric, that's conjugate dt xi dv. And now this is going to give us integral the a the t psi plus psi conjugate a the psi dt plus the psi conjugate dt dv. Okay, so I'm going to process. Now, if you recall the Hamiltonian operator, we already showed that it is given by negative h cross squared over 2m lambda squared plus v. Okay, and if you also recall the Schrodinger equation, we show that the Hamiltonian operating on the state function is the same as jh cross beside the t, which is the equation of motion. And if we rearrange this expression, then we have the psi dt to be the same as h psi j h cross. And once we rationalize this, so this will be the same as 1 times j divided by j times j, h psi j h cross, right? And this is going to give us j divided by j squared, h psi j h cross. Sorry, h cross. This is, the j is no more there. We already rationalized here. So that's h cross, which is now going to give us, this is going to be negative because j squared is the same as -1. So that's going to give us negative j h cross h psi. okay? So, which is the same as the psi dt, okay? Now, if the psi dt is the same as negative j over h cross h psi, then the conjugate, the psi, conjugate the t, there will be a sign change here, okay? So that will give us j over h cross, then h psi conjugate, okay? And if you recall the first property of the Hermitian operator, they always have real eigenvalues, okay? So soon we are going to see that the Hermitian H is a Hermitian operator, okay? Because we said all operators in quantum electronics are Hermitian. So if it's Hermitian, then it means that it does not have a J, the complex component. So we'll be able to rewrite this as J, H cross H psi conjugate. That's what I'm just trying to pull through from all that I've been saying. Now, if that is clear, then we can rewrite the first time derivative of the Hermitian operator. So now I'm going to wipe this part so I don't have to play the entire board. So we already have this. So once we plug these parameters, this and this into this and this, then the first time derivative of the Hermitian operator will become let us see. This is the expectation value, please. The expectation value of the Hermitian operator will give us there, all in bracket, the A, the T, psi, negative. So let's wipe all of this. Don't need this anymore. Minus. Now, the side T becomes minus JH cross H psi. Okay? So that's minus J over H cross. Then the conjugate of the state function. Then we have A and the Hamiltonian H. Then the state function psi. Now plus. Now we have the first time derivative of the conjugate of the state function, which is given as this, okay? Plus J, H cross, H psi, conjugate, A, psi, psi, all dV. Okay? Now, you will recall that the expectation value, say, of the position is given as the integral psi conjugate r psi dV. And when you look closely, you see that this particular component is more like the expectation value of the ADT, okay? Because we have the psi conjugate where arrow is replaced by the A, the T, then psi. So we can as well say that Going by this, the expectation value of the A dt is the same as psi conjugate the A dt psi, which is the same as this. So we can rewrite the first time derivative of the expectation value of the Hermitian operator as the A dt being the same as the expectation value, this component, the A dt, yeah, plus integral. Then we can rearrange this, okay? This minus this, because this is minus plus this. And then we see something, the J over H cross is in common. So we can bring that out of this whole expression to say J over H cross integral. Then we want to relate with this first. So I already explained why this is the same as this, because H, the Hamiltonian, is a Hermitian operator. And we know that one of the properties of Hermitian operators is that their eigenvalues are always real values, no complex components. So the conjugate operator of a real value is the same as that real value. So we can now write this as psi HA psi minus the complex conjugate of the state function AH psi dB. And if you recall our expression for commutator, then you will observe that this is an expression of the commutator AH. So we can now rewrite this in this format to say that the first time derivative of the expectation value of the Hermitian operator is now the same as the expectation value of the A dt plus J over H cross, the expectation value, because we know that this is the expectation value. So when we plug in that parameter in between this, in between the complex conjugate and the parameter, the state function itself, then we have the expectation value. So it means that this is the expectation value of the Hamiltonian and the Hermitian operator. Okay. So is this clear? Now, we already know that the quantum bracket of AH is the same as the commutator AH minus HA minus AH. So when we interchange what we have, and if you recall from what we derived in our physical lecture, that when the commutator is the same as 0, then what do we say? And if it's not the same as 0, then what is the conclusion? And that is where the Heisenberg uncertainty equation follows directly. Okay, so it means that they will be conjugate variables if the commutator is not the same as 0. But when they commutate, then it will be possible to measure them simultaneously and all of that at the same time. Well, we'll come to that shortly. We'll revise it again. But going by this expression, we can see that this follows directly from the expectation value. Okay, so we can say that this expression is the expectation value of AH. Okay, and looking at the difference between AH and HA and AH, the difference that shows us that there is the commutator. Okay, So it's more like the expectation value of the commutator. So this is a general overview of deriving the expectation value of a given operator. So what if we now want to estimate or evaluate the expectation value of the position and momentum? Because that's of interest to us, okay? We want to be able to tell the position at some point in time, and want to be able to tell the momentum of that particle. So with that, we should be able to provide the necessary or sufficient information about this particle. And we understand already that in quantum electronics, that particle is actually an example of similarly prepared particles that are probably, let's say, having the same potential energy operator, okay? Now, for us to be able to do this, we are going to invoke one theorem, the Ehrenfest Theorem, okay? Ehrenfest Theorem, okay? So let's wipe this and come back to this now. Okay, so now we want to evaluate the expectation value of the position and the expectation value of the momentum, okay? So why invoke the Ehrenfest Theorem? Because now the Ehrenfest Theorem actually bridges the gap between the classical Newtonian mechanics and the quantum mechanics. Now, in the classical Newtonian mechanics, there is a relationship between the momentum and the position, okay? And now we are saying that Ehrenfest actually postulated that, well, we can actually have equivalent values. So the position value, the momentum value in classical Newtonian mechanics could be equivalent to the position value and the momentum value in quantum mechanics should we take the expected value, the average value of the position and momentum. So that's what it is. That's what Ehrenfest said. So let us state this more appropriately. So the Ehrenfest Theorem says that the average values of quantum mechanical operators follows directly from the classical equations of motion if the vectors in the equation of motion are replaced by the expectation value. Values V and the expectation values of the corresponding quantum mechanical operators. So we are going to show this quickly because what we are trying to say is that, well, in classical Newtonian mechanics, we already know that the velocity is the first time derivative of the position, right? And then the momentum is mass times the velocity, such that the momentum is therefore the same as mass times the first time derivative of the position. And this means that the first time derivative of the position will therefore be the same as the mass, as the momentum divided by the mass. Now, this is classical, okay? This is classical Newtonian mechanics. So, but what Ehrenfest now postulated is that, well, this is going to be the same in quantum mechanics. Okay, should we take the average value of the position, that is the first time derivative of the expectation value, should be the same as the expectation value of the position divided by the mass. So this now will be the quantum mechanical equivalent. This is quantum mechanical equivalent of the classical Newtonian expression for the equation of motion. So it means that we already know this coming from the classical Newtonian mechanics, okay, that this is what we have and this is what we have. But what Ehrenfest postulated here is that should we replace this position by the expectation value and this momentum by the expectation value, then we should have something similar. So we are going to show that right quick. We'll see if it's true. We'll prove it right away. Okay, so let us start with the expectation value of the position. So let's see if we are going to arrive at this expression. Okay. So let us, I think I would love to split the board this time. Let's split the board into 3 halves. Okay. Okay. So let us consider the expectation value of the position. That is the expectation value of the position. And we know here we have to take the first time derivative of the expectation value of the position, which is the same as the x, the t. And now we already know that this is going to give us d dt integral the conjugate of psi conjugate x psi dv. And this is going to give us integral d dt psi x psi dv. Okay. And once we take this, so let's assume this parameter here is u. If we assume that these two parameters, this is u, and then this is v, then with product rule, we can resolve this, we should be able to resolve this partial derivative in the integral such that the first time derivative of the expectation value of the position would therefore be the same as integral. Put all of this psi conjugate x u, the v, that will be the psi, the t, plus v, that will be the psi conjugate, the t, x psi dv. Okay. So, but in our last lecture, which we already uploaded, you'll observe that we were able to show that the psi dt, so I wanted to recall this, we already showed it, is the same as j h cross over 2m lambda squared psi minus j h cross v psi, and then the first time derivative of the conjugate of the state function is also the same as negative, because now the sign changes, negative j h cross over 2m lambda squared psi conjugate. Now, since this is the conjugate, so we're going to take the conjugate of this, then the sign changes here, plus j h cross v psi conjugate. Okay. So what we are going to do is to replace this expression with what we have here. So that the first time derivative of the position will now be the same as this. That is psi conjugate x. So we plug in this parameter. That will be j h cross over 2m nambla squared psi minus j over h cross v psi. That's done. Then plus this expression times this. So we want to multiply s psi by this expression, which is minus j h cross over 2n nambla squared psi conjugate plus j over h cross v psi conjugate, then dv, right? So we are good. So what we now need to do is to open up this bracket. So let's show it step by step. So we don't entertain any level of doubt. So here we have jh cross over 2m. So we're bringing this out now. So that's psi conjugate x times nambla squared psi. So that will be psi conjugate x nambla squared psi. Then minus j h cross. Then psi conjugate x v psi. So the next here, now this is minus, so this is going to turn to minus, plus times minus, that's minus j h cross over 2m, which we have here. So this is x psi, s psi, nambla squared psi conjugate, nambla squared psi conjugate. Then plus times plus, that's plus. So this is going to be plus j h cross, then x psi v psi conjugate. So x psi v psi conjugate dv, right? Perfect. So now we can now rearrange this to say, now, well, one other point you should take note of also is that the position, momenta, and what have you actually obey the Hermitian operator. So when we rearrange them, they may not really affect this entire process because they are not vectors, such that the complex components may not have direct impact on them, because at the end of the day, taking the average value, are going to get an exact value. So let us do a little rearrangement here. And then we have jh cross over 2m. We are rewriting this x nambla squared psi minus j h cross, that's x v psi minus j h cross over 2m. So we can say nambla squared because nambla squared psi conjugate x psi, okay? And then let's put this together. I'll explain why shortly. Then plus j over h cross psi conjugate SV psi dv. So here we observe that this would truncate this. Okay, let's change the color. This would truncate this, and then we are going to have That's minus plus, right? So we're going to have the first time derivative of the position will be the same as the integral JH cross divided by 2m psi conjugate S lambda squared psi minus JH cross over 2m lambda squared psi conjugate S psi dV. Now, this is going to be the same. Should we bring out this out of the integral? That's J H cross over 2m integral psi conjugate S lambda squared psi minus lambda squared psi conjugate S psi dV. Okay. Now, based on hermiticity, going by the properties, you will agree with me that lambda squared, as I mentioned in our first class, is the Hessian, okay? So it is the first time derivative of whatsoever parameter we are, integrating by of the gradient, okay? So it means, and the gradient is dd whatsoever we are integrating by, such that the Hessian lambda squared is the same as d, the whatsoever d. So at the end of the day, the Hessian is a second time derivative, right? D squared dot squared. Okay, I think I mentioned, I recall I mentioned that in our physical lecture, right? So the Hessian is the second time derivative, squared d, where this could be x, it could be t, it could be any parameter, okay? So that's the Hessian, that's the lambda squared. So we'll come to that shortly. So based on this, there's no complex component there. So it actually obeys the properties of hermiticity. So we can now position this, or better still, rewrite what we have to say that the first time derivative of the position with the t is the same as j h cross over 2m, we already have here. Now, should I bring this operation out? Okay. Okay, let's just rewrite this first. Integral by conjugate x conjugate squared psi minus conjugate psi conjugate lambda squared s psi dV. So we can now resolve the Hessian of x psi. Okay. So for us to do that, let's bring that out. So we could resolve, then plug it in again. So if we bring out this Hessian, that's lambda squared. I want to bring out this Hessian. That's lambda squared x psi. So this is going to be the same as the second time derivative with respect to x, the x squared, x psi, right? And then we can solve this in sequence, step by step. So let's explode this. D, the x is the same times d, the x, x psi, right? So we're actually writing the same thing. So this time this is the squared, the x squared, right? So we want to solve them in parts. So, and then this is now going to give us b, the x. So once we resolve this, the same as product rule, u dv, right? So that will be, if this is v, u, or whatsoever, so that will give us the x psi plus the psi, the x. So the x is going to give us psi. This is going to truncate this. So this will truncate this, so it reduces to 1, so that's psi. So then we'll come to this again, d, the x, which is this, in brackets, psi, plus the psi, the x. Okay? So we now have to resolve this partial derivative, okay? And once we do this, so we're going to have this will become the psi, the x, that is this, then plus d, the x, into bracket, the psi, the xx. Okay? And once again, we can resolve this, say this is u. Let's say this is u, and this is v. So the u, the v, then we'll be able to resolve that again. And then we are going to have the psi, the x, which is this, the psi, the x, plus, let's say the psi, the x, u, the v, the x, right? Plus the squared psi, the x squared x. So this again, we truncate this, and this will reduce to 1, right? So we have the psi, the x. So in other words, we have the psi, the x, plus the psi, the x, plus x, the squared psi, the x squared. So this is going to give us 2, the psi, the x, plus x, the squared psi, the x, as the Hessian of x psi, right? Now, if this is clear, so it means that we now have to plug this expression into the first time derivative of the expectation value. So if I made me to wipe this part. Okay. So now when we plug this into the first time derivative of the position, expectation value, then we have that JH cross over 2n integral psi x number squared psi minus so the psi conjugate times this entire process, that will be minus psi conjugate times twice the psi the x plus x the squared psi the x dv. Okay. And then once we open this up, so we're going to have JH cross over 2n integral psi conjugate x sigma squared psi minus 2 psi conjugate the psi dx, then minus, this is minus here, minus times plus minus psi conjugate x the squared psi the x squared. Okay. Now recall that, excuse me, please. Now recall that the Hessian is the same as the square, so such that this expression here becomes sigma lambda squared x psi will be the same as 2 the psi the x plus x lambda squared, because this is the squared psi the x squared, right? That's what we have here, the squared psi the x squared. So that's x lambda squared. So if that is what we have, then we can replace this expression by lambda squared, okay? So this is squared here, right? So we can replace this entire expression by lambda squared. So I'll just wipe this and replace it with lambda squared. X lambda squared, which is what we have here. Okay. Psi, coming. That's lambda squared psi, right? Because the squared, the x squared is the same as lambda squared, and then this is psi. So we're going to include the psi here. Perfect. So I think we're in good shape now. So now if you observe this, you realize that this expression and this expression are the same, right? So they will truncate each other. Now, okay, let's use a different color for that. So you see that this expression and this expression are the same plus minus, and then this 2 will truncate this 2. So what are we going to get? So the first time derivative of the expectation value, x, the t, will be the same as negative, because this is negative, jh cross over m integral psi conjugate the psi the x dv. Okay, and now you recall that in our last lecture, which you already have online, that we show that the expectation value of the momentum is the same as negative jh cross integral psi conjugate the psi the x dv. And you realize that the entire expression here, other than m, is the momentum, such that the first time derivative of the expectation value of the position is therefore the same as the expectation value of the momentum divided by m. And this is what Ehrenfest said, just like the same way, if you recall what we stated earlier, that this is in quantum mechanics, okay? Quantum, okay, let's use a different color so to make it look obvious. Now, in quantum mechanics, this is in quantum mechanics. While in the classical Newtonian mechanics, we saw that the R, the T is the same as P over M, okay? And according to Ehrenfest, should we take the average values or the expected or expectation value of R and of the position and momentum, then we get something similar in quantum mechanics. Hence, we just derived what Hermitian said, okay, to show that, well, Hermitian was not just making some assumptions. So going forward, we can now say, since we're able to show that the first time derivative of the expectation value of the position is the same as the expectation value of the momentum divided by m in quantum mechanics, while in classical mechanics, the R to T is the same as the momentum divided by in classical mechanics. So going by this, we can therefore say that according to Ehrenfest Theorem, the classical Newtonian mechanics, let's write that, Newtonian mechanics, or better still, equations. Let's put it that way, Newtonian equations of motion are obeyed if the vectors appearing in the equation of motion are replaced by the expectation values of the corresponding quantum mechanical operators in quantum mechanics. Perfect. I think that's what it is. Okay. Okay. So we can also do same with the expectation value of the momentum. Okay. In the x direction. So let us look at that quickly before we move on. So let us look at the expectation value of the momentum. So if we also take the first time derivative of the expectation value, so we know that we have JH cross, then the expectation value of the commutator between the Hamiltonian and the momentum. Okay, we already showed this earlier. So this is going to give us JH cross integral psi conjugate. Then where we have the Hamiltonian, which is negative H cross squared over 2m Nambla squared plus the potential energy operator, then minus J H cross psi dx, d dx. No, let's be consistent. We use a square bracket here, so that psi. So this psi conjugate psi gives us the expectation value of this parameter, the NDV. Okay. Now you recall from, I wanted to recall from what we just showed. I think this was was it last week? This week, that, yeah, I think last week. That the first time derivative of the Hermitian operator is the same as the expectation value plus J H cross integral psi conjugate HA psi minus psi conjugate AH psi dV, where we have the expectation value of the A dt plus J H cross the expectation value of A, the commutator dV. Okay, so if we evoke this parameter, then we should be able to represent this in this format. Okay, and then I will just run quickly because we're running out of time. Then going by what we already did, then the first time derivative of the expectation value of the momentum will therefore become psi conjugate V the psi dt minus psi conjugate d dx V psi dV. Okay, and from this we can resolve this using your product rule. Then this will become integral psi conjugate V the psi dt minus psi conjugate dV dx psi plus V the psi dx, right? The psi dx dV. Okay. And once we open this up, so we are going to get the integral psi conjugate V the psi dt minus psi conjugate, this times this, dV the x psi minus psi conjugate V the psi the x dV. Okay, and then we'll see that these two expressions will cross out, this will cross this out, so we have the integral negative psi conjugate dV dx V psi rather psi dV the psi. Sorry, I think I crossed out the wrong component. Sorry. Is this and this minus this. So we are going to have the integral negative psi conjugate dV dx psi dV. And you already know, once we have this, so this is going to be the expectation value of dV the psi, because we have psi conjugate psi and this in it. So this is going to give us the negative of the expectation value of dV dx. Okay, and the assumption we put up here is that the Hessian and the conjugate commutate, okay, or commute. They commute rather. They are, you know, once we get the commutator. And also, we already know from the classical Newtonian mechanics that that the first time derivative of the momentum is the same as the negative nambla v. Okay, so that we can show. Okay, now that we have done this, I want to quickly run through what we did in the physical lecture. Okay, just before we run out of our lecture. Okay. Now, recall we made mention of the three postulates. Okay, just to recap, like some of you made mention of, we said we have our postulate 1, which has to do with the state function. And then postulate 2, I'm going to come back to the expectation value. So what we just did was to show how to evaluate the expectation value. So now that I want to talk about the postulates, so we'll see how the expectation value brings us to Heisenberg's uncertainties or uncertainty principle. And then that now gives us enough information to know that, well, we cannot, when we want to measure the momentum and position, unlike in classical mechanics, the more we know the more we know about the position in the quantum mechanical perspective, the less we know about the momentum, okay? And then the postulate 2 has to do with the operators. We already made mention of all of this in class, so let's just run through it quickly to clear all doubts. And then here we deal with the equation of motion, okay? So what did we say the first postulate is all about? Okay, so postulate 1, which is the state function, okay? State function. So we've been playing with the state function, we've been playing with the operators, likely because we already made mention of all of these, okay? So now, the first postulate actually states that the state of a dynamic system is completely specified by the state function, okay? So the state of a dynamic system is completely specified by the state function. Okay, and here you recall that we designated the state function to be psi, and since it's a complex quantity, then it means it has a magnitude, and then it has a phase, okay? And looking at this, this also will bring us to the wave particle duality problem, which we are going to resolve shortly. So a fundamental distinction between the classical and the quantum mechanics is that in classical mechanics, the state of the dynamic system is completely specified by the position and velocity of each constituent part of the particle. And the idea is that the position and velocity of a particle can be measured and specified simultaneously in the classical perspective, okay, at each instant of time. And it means now here, let's say one to put that in a different way, we say that the position and velocity of the particle at one instant of time are completely determined by the position and velocity of the particle at some previous time. That makes it a dynamic system, one. And then it means that it is deterministic, largely because objects can be seen, they are very large, and this is the macroscopic dimension. So if two particles, for instance, are not at the same place or not moving at the same velocity or with the same velocity, they are obviously not in the same state in the classical perspective. But in quantum mechanics, we now have to go into the subatomic or atomic dimension. And there, the position and the velocity of a particle cannot be measured and specified simultaneously at the same instant of time. So the idea is that in quantum mechanics does not actually presume that measurement of position of a particle will necessarily yield a particular value predictably. And this brings us to the average value, okay? So should we now, for instance, say that, say a particle is specified by a given state psi. Now, the most specific information on the position of that particle by measurement is that the probability of getting x1 relative to s2 will be given by the probability density function, the ratio of the probability density function of x1 relative to the probability density function of s2, okay? And we already know that this is the same as the psi of x1 conjugate times the psi of s1, right? We already established this, okay? That is the PDF, okay? Why this is the same as the psi conjugate of S2 times the psi of S2. We already explained this in class, okay? And should it be established that only one particle exists in the spatial range, say from x equal to 0 to some value x equal to m, then the probability distribution function psi of x squared will be integrated over that spatial range between 0 to m. And since we already know it is one particle, then we are able to get the exact value of 1. But should we consider n particles, then this will reduce to n. Okay? And if, for instance, the wave function is normalized, then the absolute value of the probability of finding this particle in the range from, say, x to x plus the x will now be the same as the probability distribution function dx. And in our last class, we were also able to express the expectation or average value, okay? The expectation, which we have been playing with, the expectation or average value to be given as this of the position. And there we were able to specify that the expectation value of the position, is the same as taking the integral, given the limit, say 0 to m, psi conjugate xx, then psi conjugate on the x, which is the same as the integral of x times the probability distribution function, okay? So this is just a recap of what we mentioned in class. And then, should we take the mean squared deviation? The mean squared deviation, then we have, no, not lambda, we have delta. So we have delta x squared will be the same as the integral taking of 0 to m given the limit. Now psi conjugate. So we have this process here times psi conjugate dx. So since it's the mean squared, so we have to take the difference between this and the expected value, okay, or squared, okay? And then this is going to be the same as 0 to m sigma. Okay, let's not, let's put it differently, x minus the expected value squared, then the probability density function, okay, squared dx. And technically, this gives the measure of the spread of the probability distribution, okay, the spread of this probability distribution around the average value. And then we are also able to specify the recording is okay. And now we know that the uncertainty is given as lambda or as delta squared, which is the square root of the mean squared error, okay? Which is the uncertainty in the position of the particle when it is in the state defined by the state function, okay? And this now is the same as the expectation value, the difference between the expectation value of x squared minus the expectation value squared, then or square root. So from this, we can infer that, you know, by way of interpretation of the state of a dynamic system in quantum mechanics that it is strictly probabilistic and not deterministic, okay? And you should also know that the state function satisfies the principle of superposition, such that should we have a state function A, psi, then it's going to be the linear combination of all the state functions plus phi 2, psi 2 plus phi 3, psi 3, all the way, okay? Where alpha 1, alpha 2, all the way are complex numbers. Then we talked about it last time, and then we also made mention of the operator, okay? Now we said the operator is that parameter that is able to transform the function from one state to another. And now you see that for the operator, this states that all physically observable properties of a dynamic system are represented by dynamic variables that are linear operators, okay? So that is, say, let's put it this way. Let's just like we've seen, the Hermitian operator operating on the state function will give us, you know, another state function. And here we made mention of two corollaries, okay? So we'll just state them briefly. We mentioned two corollaries here. And for the corollary one, we mentioned that all dynamic variables and their corresponding operators representing any property of the system have the same functional dependence on the canonical variables representing the position R and the linear momentum, the linear momentum P. Right. As in classical mechanics, okay? So here, the operators represented the kinetic energy, the angular momentum. So the kinetic energy, for instance, T hat is the same as P squared hat over 2m. And the operator representing the linear momentum is the same as L hat, which is the same as LR hat cross P hat, vector P hat. Then, and the operator representing the potential energy is the same as L hat. And then the operator representing the Hamiltonian is H, which is the same as the sum of the kinetic energy operator and the potential energy operator. And then the second corollary, which we have been playing with, which you already mentioned in class, is that that's corollary 2, that in Schrodinger representation, The operator, the operators representing the position, coordinates, S hat, Y hat, Z hat, or arrow hat vector are the ordinary physical Cartesian components. X or physical, no, they are the ordinary physical variables. Let's put it that way. Variables. Physical variables. S, Y, Z, and even R, okay, the vector R. And then for the momentum, P, X hat, Y, Py hat, Pz hat, then they are represented by their differential operators. That is, Px hat is the same as negative J H cross D dx. Then Py hat is the same as negative JH cross D dy. And Pz hat is the same as negative JH cross D dz. So technically, the momentum can be represented as negative JH cross Nambla, which we have been playing with ever since, okay? And then we were also able to play with the commutator, okay, in class. And then we were able to show that the commutator between, which we also have in previous videos, that the commutator between the position and the momentum is the same as JH cross. So we're able to show how this works. And then we were able to also hold the Schwarz inequality that the, should we take the product of the uncertainties, okay, of two operators, then we say that it is greater or equal to half or 1/2 the magnitude of the expectation value of the commutators, right? And we already played with this, which is approximately equal to 1/2 of the expectation value of the commutator. And then we're able to see, going by this, that the uncertainty product between the position and the momentum is greater than or equal to some parameter. Since it's not the same as 0, it means they don't commute. So then this brought us to the Heisenberg uncertainty principle, the Heisenberg uncertainty principle, which states that it is not possible to know or to specify the position and the linear momentum in the same direction of the particle simultaneously. So the idea is that the more you know about the position, the less you know about the momentum. and vice versa. Okay. And then we gave a few interpretations and then talked about the eigenvalues and the eigenvectors. And then we also made mention of the third postulate, which is the Schrodinger equation. So I think we'll conclude our class here today. That's postulate 3, which states that all state functions satisfy the time-dependent Schrodinger equation, which we have been playing with, which is JH cross psi dt, which is the same as the Hamiltonian operating on it. Okay, where H is the Hamiltonian. Okay, and then this will bring us to the time-independent Schrodinger equation, and probably we'll begin to talk through from there in our next class, and then see how far we'll be able to go, so I don't take you into your next class. Okay, so I think this is a good place to start, and I'd love to take 1 or 2 questions short, briefly before we call it a day, so you could get into your next period. Any question, please? Okay, I can see one hand. Go ahead, please.
Are we going to be recording the lecture?
Are you what?
Going to get the recording
Yeah,
of this lecture?
sure. That we recorded, so you're going to get it. I'll try to upload it on my channel right away. Is that clear?
Yes, sir.
Okay, so I think at this point we'll call it a day. So we'll meet in our next class. Bye for now.